Today, I will present how to harness the power of artificial intelligence to help us predict the wildfire-induced fragility of structures. To begin, let's first define what is wildfire-induced structural fragility in our topic. This timeline presents several key time points in a wildfire. Let's say wildfire is ignited in the first time point and then detected by someone or some devices. After receiving the wildfire report, let's say the firefighters, they will take immediately actions to and arrive at the target structure soon. For the wildfires, it may gradually approach some structures and ultimately damage them at a time point. Now, let's introduce two concepts, structure failure time and the fire response time, to define the wildfire-induced fragility. The first concept, structure failure time, it is the time from detection to the structural damage, which presents how much time our structure have left to be damaged by wildfire. And fire response time is the time from receiving the report to completing deployment, which shows how fast our firefighters are moving to stay ahead of the wildfire. After defining these two concepts, we can define the wildfire-induced structural fragility as the probability of the fire response time exceeding the structure failure time. Now, let's take a look at the factors that can affect the fragility of our structures. Here are listed 4 aspects: vegetation, environment, especially wind speed or direction, terrain slope, and fire resistance performance of structure. They are all important variables that influence our structural fragility. However, when assessing such fragility, how to quantify these factors is a more important issue compared to the factors themselves, because this is directly related to the accuracy of our results. For most factors we mentioned here, they can hardly be represented by a deterministic or constant value. That is to say, for example, let's say today's wind speed is 3 meters per second. Here, 3 meters per second is a deterministic value. But is wind speed always constant? Of course not. It fluctuates constantly. Our research findings indicate that this fluctuation can have a significant influence on the fragility. In the next slide, I will show how to take such fluctuation into account when using artificial intelligence to predict our fragility. So before introducing artificial intelligence, let's say the common step for assessing our structural fragility. In the first step, we need to collect data to assess the vulnerability of our structures. This data represents the vegetation conditions, environmental conditions, terrain slope, and fire resistance performance of our structure when wildfire occurs. In the next step, we analyze this data by using numerical simulation or experiment. During the analysis, we can collect the response data that we are concerned about. For example, the temperature, the radiation intensity, the wildfire arrival time, or the wildfire spread time, or the wildfire spread speed. In the final step, we can calculate the fragility according to our collected response data. In simple terms, we collect input data and then analyze them to obtain the output data. If our input data fluctuates and is non-deterministic, then our output data is also varying. The power of using machine learning algorithm is that it can obtain the relationship between the collected varying input data and the output response data. According to this relationship, we can rapidly predict structural vulnerability and any situations. This ability can help us always stay ahead of wildfire. The predicted results could be displayed on, for example, on the mobile devices and support an efficient preparedness plan for the stakeholders involved in wildfire. This slide shows how to use machine learning technique to predict the structural fragility. In the first step, we employ ArcGIS to extract data layers that we are interested in, like the traffic network, the location of critical infrastructures, building structures, and the distribution of vegetation types. These data layers are then combined into a final integrated dataset. To make the terrain slope into account, we also incorporate a digital elevation model. In second step, we use the multi-physical simulation platform to simulate the wildfire spread. We can record the response that we are interested in, like the burnt area, the wildfire spread speed, and so on, to be as the output response data. The final step is where the machine learning comes into play. We feed the input data coming from ArcGIS and then output response data recorded in the multi-physical modeling into the machine learning algorithm to obtain the inherent relationships between the input and output. With the established relationship, we can further make any prediction. Now, we will use the Koan community as an example to showcase how machine learning algorithm can predict structural fragility. The Koan is situated approximately 50 kilometers north of Sydney, with the Pacific Motorway and highway passing through it. As we can see from this image, the community is surrounded by dense vegetation, indicating a high wildfire risk. Firstly, we employ ArcGIS to extract different data layers. Here we extract the distribution of vegetation types, the traffic networks, the location of building structures and infrastructures. Then we integrate the data layers into the digital elevation model to form the final digital twin model. Subsequently, we harness the power of multi-physical platform to simulate wildfire spread on this model. The right figure shows the possible burnt area at a specific time point that our machine learning model predicts. The darker the area, the higher the probability of being burnt. Now, let's focus on a single residential structure within the Koan community to assess its fragility. Here, we'll assess the fragility of three structural components: window frame, wall, and roof. These three components are constructed, let's say, from various materials and have different time limit. That means they have different level of fire resistance. Let's say when the temperature they suffer first exceeds their temperature limits, they will be predicted to be damaged. Of course, we can use other methods to define at which conditions the structure are damaged. Here, I just provide an example. Let's say the fire is ignited from this red line and approach to structure. Right table lists the input variables that we considered here. They are all non-deterministic. It can be found we have taken some specific vegetation parameters and wind speed into account, like vegetation moist content, vegetation fuel load, vegetation height, and so on. We installed sensors on the structure components to record the structure temperature as the output response data. As shown in the line chart, as the wildfire approaches the structure, the monitored structural temperature is continuously increasing. Additionally, we can find that due to the uncertainty in vegetation and weather parameters that we have taken into account, the observed temperature changes have also become non-deterministic. Here, the structure failure time is no longer a time point, but a time interval. That means our structure could be damaged at any point within this time interval. For representing such non-deterministic wildfire scenario, we run 1,000 samples to build our dataset with input and output. Then we use the machine learning algorithm we developed to obtain this relationship between input and output data, according to the obtained dataset. Here, we use this relationship to predict the structural failure time. In the upper figure, the red point represents the actual structural failure time we recorded from 1,000 samples. The blue point is the predicted structural failure time. We also compared our predicted structural failure time with the actual time to verify the accuracy of our predictions. The comparison results indicate that the maximum relative error is only 4%. I think this is not a bad result. Finally, we can draw our fragility curves according to the definition of fragility. Additionally, our machine learning model can also empower us to make any predictions according to newly generated wildfire information. Here, we generate 3 new wildfire scenarios by revising the input data. We can continue to feed them into the machine learning model as input data to obtain an updated fragility. This capacity, as we mentioned above, can help us stay ahead of wildfire at all times and enhance our ability to plan and prepare for potential structural damage. Our machine learning aided fragility assessment framework can help us identify the most fragile structure within a community. Armed with this identification, we can optimize the deployment of firefighting forces. This ensures that resources are directed where they are needed most. Ultimately, the framework can also contribute to the broad target of building a more resilient community. To sum it up, our multi-physical simulation platform, coupled with the machine learning algorithm, equips us with predictive capacity to enhance our understanding of wildfire behavior and structural fragility. It will be helpful to build a more wildfire resilient Australia and ultimately achieve a sustainable development. Till now, our research work has been supported by several Australia Research Council projects. Here is our research groups. That is the end of my presentation. Thanks for attention.
Daniel, thank you very much for the presentation. I find it fascinating, and I'm thinking about its applicability. Have you investigated the potential to link that sort of research with automated triggering of sprinklers or deluge systems on dwellings in the situation where the owners or the occupiers have chosen to leave the site for safety reasons and leave the system to run itself?
Yes, definitely. Thank you for your question. I think this is a very interesting point, and we will consider in the next step. But till now, we just provide a very early stage framework. Yeah, maybe in the future we will take this into account.